This video is going to look at a related rate problem involving a conical tank. And just to review here, a conical tank, all we're talking about is a cone type shape. And the example tells us that we have a conical tank with the vertex down, and it is 10 feet across the top. So here our tank is 10 feet across the top. And 12 feet deep. So that tells us the tank then is, and this is indicating the whole tank is 12 feet. Water is flowing into the tank at a rate of, so we know that 10 feet across the top, the tank is 10 feet deep, and water is flowing into the tank at a rate of 10 cubic feet per minute. Now, since we're talking about 10 cubic feet per minute, we have the water flowing into our tank. And that tells us it's going at 10 cubic feet per minute. So if that's the case, that means our volume here, as this water flows in, this volume is going to be changing 10 cubic feet per minute. So that's the rate and change of our volume of the water. And they want us to find the rate of change of the depth of the water when the water is 8 feet deep. So here they're telling us the water is going to be 8 feet. So the depth of the water is 8. So all of this is our given information, and we want to find the rate of change of the depth of the water. Okay, so if that's the rate of change of this height of the water, then that means we're looking at finding dH dt. And we've pretty much labeled everything that was given, but if we kind of review what's given here, we know that the height of the water is 8. And we know here the tank has a height of 12. So we know that here the h is equal to 12. And all the way across here is 10, so the diameter is equal to 10. And we know that dV dt is also equal to 10, so that's the rate of change of the volume. So we need to come up with a formula that's going to relate the given information and the dH dt that we want to find. Well, it should be pretty obvious that if we're looking at this conical tank, we're talking about this rate of change of the volume, so we're going to have to use the formula for volume. And volume for a conical tank is simply going to be 1/3 pi r squared times the height. So now if we think about this formula, realize that if we take the derivative here, eventually when we take the derivative of v, we're going to have dv dt. When we take the derivative of the r, eventually we would have dr dt. And if we take the derivative of h, we would have dh dt. And if you notice, if we take the derivative with this problem, we have r squared times h, which would require the product rule. Now, if you notice, dv dt we have, dr dt we do not have, and dh dt is what we're looking for. So if we take the derivative in this form, we would end up with this dr dt, but we don't have the rate of change of the radius. So it looks like is there some way that we can eliminate the variable r before we take the derivative here? Well, if we look at this here again, let's label just the height. We know that the height here of the entire cone is 12, and we said that all the way across is 10. Well, that tells us then that this means the radius would be 5. So if we kind of think of your similar triangles here, if we're looking at this ratio here of we have the radius to height, we know that the radius to our height would be equal to 5 to 12. Okay, so we know R to H is equal 5 to 12. Then if we solve for the radius, we would end up with 12R is equal to 5 times H, so therefore R is equal to 5/12 H. So that gives us a representation of the radius in terms of H. So if we substitute in the 5/12 H up here, we would then have, in place of the radius, we would have volume is equal to 1/3 pi times the 5/12 H, and we have to remember to square that, times the height. So now the advantage of doing this, we now eliminate the variable R, so now we just have the volume in terms of the height. So if we simplify this, volume is equal to 1/3 pi, and if we square this, we would have 25 over 144 H squared times H. And before we take the derivative, we could continue to simplify this a little bit. Now I'm going to leave the 1/3 out front, and you'll see why I'm going to do that here in just a little bit. And then we'd be left with the 25 pi over 144 and H squared times H would give us H cubed. Okay, so this is probably simplified far enough. So now if we take our derivative, again, we're taking the derivative with respect to t, so we would have dv dt. And now all of this is just a constant. So we're going to take our exponent 3. Well, if we multiply that to the constant, that's why I left the 1/3, because 3 times 1/3 is 1. So that's going to cancel out the 1/3, so we're left with the 25 pi over 144 H squared. So multiply by the 3, decrease your exponent by 1, so we get 25 pi over 144 H squared. And we're taking the derivative with respect to time, so that means we have to take the derivative of H, which then would be dH dt. So at this point we have our derivative, and now all we have to do is our substitution. So if we substitute in our given information up here, we had dv dt is 10, (25 pi over 144) times the height. And our height, remember we were looking at the height here, the given height of the water at this point is 8. So that's 8 squared. And then dH dt is what we're looking for. So we can simply solve this for dH dt, and if we do that here, we would end up with 10 equals let's see, 25 pi over 144 times 64 dH dt. And if we simplify this, you could certainly do a decimal. I'm going to leave it as a fraction. If you multiply this out, you're going to get 100 over 9 pi dH dt. And if we divide all of this away, then dH dt is going to be equal to 10 times 9 over 100 pi. And if we simplify this, 10 over 100 is going to reduce down, so we're left with 9 over 10 pi. And this is the rate of change of the height with respect to time. 9 over 10 pi. And what will the units be? Well, up here we were using the units were feet. So that means our units would be feet per minute. So that tells us at the instant that our water level is a height of 8, the rate of change of the height is this 9 over 10 pi feet per minute.